can see this orange arrow actually going linear in the rotating frame, tipping the magnetization to the y-axis. And to hear that, you just turn on the hearing button, which acts as your receive RF coil. And then you can see the sinusoid plotting, sinusoid and cosinusoid mixtures depending upon what's the angle of your RF transmitted pulse and where you're listening. Relative to that, you should be able to see sinusoids and cosinusoid getting plotted here. You can change a bunch of these things and look at it not in the rotating frame but in the laboratory frame of reference. For those of you who've not looked at either looking at these vector diagrams, the idea is for you to be able to get a sense of how magnetic field strengths, like the two different magnetic fields, at least in this B0 and B1, interplay and what does that do to your magnetization. So this is one game where at least the undergraduate students that I've been working with feel very excited because they can make the connect from a textbook to what's happening in reality. And you can open and play around. There are a few questions to answer to see and get those 5 stars here as well. For the beginner, the last module was to mostly demonstrate this famous experiment by Paul Lauterbur, which is to look at the effect of gradients in general. And we have a bunch of different models loaded up here where you can actually select the kind of, where you have the select model. You can select a bunch of 3D printed models that we actually have and load it up into this game as CAD models. And then be able to play around with the direction of the projection shown by these purple lines, and then see how the 2D projection of all of that, which is sum total, look like, and at the same time the 1D projection as well. So this is to demonstrate the ideas related to imaging gradients. So these are for beginner games. We also have advanced games for each of them. Those would be the, games 2, 4, 6, and 8. Looking at the effect of K-space, flow, trying to see if you can actually map T1 and T2 of tissues, and then trying to do mostly like an image reconstruction with projections. So those were the 4 games that I wanted to talk about. Just quickly going to, here's another demo where we're looking at K-Space Magic, where you can actually draw your own object. You can doodle whatever you want. Basically you doodle here, and then you can apply filters to your doodling. It will basically make an image, and then on the right hand side you can draw your own filters, which is basically how much of K-space you want to keep, and that will essentially show you the effect of more 2 things. One is the Fourier transform pairs between the image domain and the and K-space, and also some level of image processing itself in terms of low pass filtering, high pass filtering, and the like. So this is another cool app where you can actually look at different windows and filters for both K-space and image domains to get a good sense of how it looks. Giva here, I think she's been trying to draw a bunch of random stuff and see, what will happen if you basically acquire only the center part of K-space. So you mostly get a blurry image. You can see that the edges are not well defined on the left. So you go back and forth between the image domain and the K-space domain. And like I was mentioning, when you're actually looking at this, in this case, this is in the laboratory frame of reference, you can see that the rotating frame is unchecked. So you can actually see a sinusoid happen. And this is the coolest thing. If you also have hardware to go along with this, which is what we're working now, to be able to show that the same phenomenon happens in hardware when you build your own hardware, if you get it right. We've tested this on a bunch of different populations in a bunch of different movies. I'd like to see if you guys can. I don't think we are in the position where I can even show you the feedback. I'm going to try one last time to see if the server is actually rebooted. So I'll be the only one to play. Looks like an issue with the admin. I last time did not think through that. Want to demonstrate. So we have 21 minutes, so it's not that bad. So as I was talking to you guys, here's um, here's the instructions. I'll try to follow this just with a quick yes or no. Could you let me know if there are students here who are interested in MR physics in general before actually I go and figure out how much time to spend on this?
I think
Maybe
you
in the
can
chat.
you can briefly, yeah, cover some basic physics if you want. Yeah.
Sounds good. So,
Yeah.
um, so traditionally, what happens, probably in the next 7 8 minutes, right? So traditionally, what happens is we have a bunch of very good books, and they give you good pictorial representations in the rotating frame of reference uh, to get you going in terms of understanding what happens. In the case of games, what you do is, like I said, this is my magnet, and let's say I want lesser magnetic field strength. I basically set that. You see that the net magnetization vector m0 is reduced, right? And then the good thing is there are instructions that give us shown that you don't have to necessarily work your way on the UI. So you can turn off the V0 and then turn the slider to change the strength, which I just did. Um, so the question then is, if one Tesla is 10,000 Gauss, what am I at? I am at 45 Gauss. So it's 45, into 10 to the power minus 4 is my magnetic field strength. So that's the magnet bit. Then, as you see, you would have earned a star once you finish stuff. Now, setting this up for precision. So for precision, now I'm going to look at 45 degrees. Okay. So I'm turning on the magnet, setting it to 100, let's say. And then I'm setting my RF. So you can see the RF actually getting turned on. And then right now it's at 90, doesn't matter. So if I say a tip, um, set, my magnet is not turned on. Okay, there we go. There we go. So I was trying to basically play an RF pulse without the magnetization being on, which is kind of silly. But you can see in the vector diagram that it basically tips to the y plane, and this was in the rotating frame. If I basically reset this and make sure that I select what I need to select, and then do this tipping, so I should be able to, let me set it. So we should be seeing the whole thing going around. So I was trying to basically play an RF pulse without the magnetization. turn this on, tip it. Reset. No. The 180-degree pulse. Coming back. Okay. Then if I have my magnetic field in X, and then transmit, I receive, I should be able to see a waveform. Looks like I'm hanging up here. So when the magnetization is actually in the XY plane, you do see that you're getting a sinusoid. Looks like there's some unique combinations where I think the software kind of bugs out. But essentially, this is what you would expect when the magnetization is in the XY plane and you're actually receiving. So yeah, I was trying to preempt. I think there's the RF pulses here, which we kind of tried. Turn on the rotating frame and the red transmit field to enable the RF pulse. So I'm going to stop this and then try to play. So let me just reset my magnetization back to Z. And okay, click. Reset. There's some bug in here which is not letting me do what I want to do consistently. But essentially what you would want to see is once you have this 90 degrees flip, you should be able to see the magnetization tip. Looks like the bug is with the laboratory frame, not happening continuously. Then you can explore with different flip angles. If I reset, everything goes back to being what it was. I can play another flip angle like I showed you. I tried 180, but I'm going to try 45 now. And I need to turn on my rotating frame. So it's about half the magnetization that you actually see. Maybe more, 3 by 2. Sine 30 is half. But this should give you a sense of the vector diagrams in terms of how we want to do this. You can also pulse this RF in um, pulses RF in different directions. Like if you want to do it on the y-axis instead of z-axis. Okay, there we go. All right, so you finally get to see the laboratory frame of reference, which is how you would see the magnetization once you get onto the rotating frame. You should be able to see now I'm shooting from the y-axis, and that's my magnetization vector from before. And one of the things that I like to do is to do this, which is uh, the gray vector is where you want to actually do. This is an assignment. So let's say my initial magnetization vector is on the y-axis, and I want to get back to the target is z-axis. How would you go about doing that with a control of RF? Um, so you could actually, for one example, do like a 270-degree pulse on the x-axis, and that should kind of get you to there. But and that's how you complete that exercise. But you could imagine different things where the exercise is now you randomize, you keep getting this initial magnetization and final magnetization vector positions, and based on your knowledge of the RF pulse and how you want to play that, you want to get that back. I think Geva says in about 3 moves. It depends on your understanding whether you want to do 3 or fewer. Um, but that's the general sense of the game. And once you're done with these games, then you can play the quizzes and see if your knowledge of handling these very simple simulations with block simulators and figuring out the effect of rotations can be done. The last one is on the projections. Like I was explaining to you, based on the publication, you can load a bunch of 3D models here. So maybe I'm going to use something like a double cone um, and load the model. So you can also, you can see what's inside. If you click on the transparent, you can see what's inside. And then you can do a 2D projection and the 1D projection. I'll pause here because I'm going to go back quickly and get a sense of where we are with what we're understanding. But in general, the idea is you can shift around and do these projections in different axes and check how it looks, and also get the sense of understanding projections when you get to the lab manual. I think there's quite some effort put in, which is kind of verbose at this moment. But to give you a sense of what is 2D projection, what is you know the effect of doing some of this all the way from XSC2 and back, and how it's used. I think what I like about this is, in general, the effect that you can actually choose a whole bunch of different models. You can, if you download the full code, you can actually add your own model. The lines basically show in which direction you're computing this projection, meaning summing in that direction. So these visual examples give you a sense of understanding projections, which is very fundamental if you look at it in terms of the whole image computation in MR, traditionally from CT, but even in MR, where you apply readout gradient to the echo that you acquire. And that essentially on Fourier transform is a one-dimensional projection of the object along that axis. So this kind of reinforces those ideas. We are now building some hardware to go along. So the scan is not functional yet. The calibration, again, is a bunch of calibration games when you have that hardware. Um, so we have a tabletop MR system that comes from MIT Martinos that we are tweaking, and this is to interface with that. So hopefully in a few months to a year, we'll have some hardware to go along with this as well, where you can do your real-time shimming and have a small benchtop scanner next to you, where you can try out your cool ideas on pulse sequencing or image analysis and get some initial data before you actually go to the real scanner, what people call as a target. But in this case, you actually have a mini tabletop scanner at 0.35 Tesla. So that's mostly about the games. Sorry that it was a little buggy. I made a mental note of some of those bugs, um, but feel free to actually uh, report bugs here under issues. Um, so just going to quickly post that link. Yeah, we're testing out the Heroku right now. And I think I already see a bunch of bugs there, but I'll be happy to hear. There's also some feedback. If you don't want to do this on GitHub, we also have a feedback page, which I will quickly send you a link. Okay, so I'm pulling out the link for the Google form. Please be as forthcoming and providing, so you can actually tell us issues on the tool overall, including the web deployment. And then I'll quickly return to my slides, which is mostly to thank the folks who put this together. And wait for some question answers. Okay. So most of the backend coding is being done by Gehua. A little bit from Marina on the front end in the initial days in 2019, 2020. Ivan's work I haven't shown you here today, which is all related to the hardware and modularizing some of these coils, which I haven't shown you here. A bunch of different collaborators from different parts of the world, and of course, funding sources both from the industry and from NIH and some foundations. So these are my coordinates. We have other open source projects too that I haven't spoken today, related to pulse sequence development or simulations of fingerprinting and things like that, which are available here. We are also part of a low-field community project to build our own scanners and other publications here. So with that, I'll pause and thank you for your patience during the rebooting of the Heroku server, and let me know if you have some questions.
I have a small technical question. Why do you limit to 100 Gauss only?
Oh, no, that's a good thing actually. We could actually pull in and make it 3D. The reason we want to do 100 Gauss is to go along with the hardware. Basically, yeah. So that's our main intent. Actually, it should go up to 0.35 Tesla now.
Yeah.
Because, yeah, but you're right. From a simulation standpoint, you don't have to necessarily restrict it to a number. We did think about percentage at some point, but then the T1s and T2s that you'd be getting would be different on a percentage, but it should actually get to 0.35. Right now it's like 10 very little. Any other questions or inputs? Even if it's in the chat, I probably see somebody's typing something. So I'm just going to.
Any questions? So, do you suggest any other like open source, like yours platform, who can also be used for teaching point of view? Like I know there are kind of a couple of block magnetization stuff by Germany group.
So yeah, that's a great question. So we've in the article we've actually compared existing software. There's like a table. Let me just see if I can pull that out. I think that's a good question. I don't know if anybody's looked at it from a game standpoint, but I do know that people have actually looked at providing simulators in general. The most famous one that I think, to me, is the one that is relevant is Gemris, which is probably the most fully functional simulator. Other than that, in terms of question answers, MRI question answers is probably the one that we link to.
Yeah.
For getting it. Yeah. So you see the supplementary material on this article that I shared, it should give you a table. Let me just get to that quick. Okay. So
could you please share the article? Could you please share the article?
Yeah. So the article was shared as a QR code. Let me just quickly share. Yeah, let me know if you see my screen.
Yes, we can. Yeah.
This is the NMR in biomedicine article on this simulator. So
Right.
it can run in a bunch of different options. Like I said, virtual machine, log, or the web. The web is looking clunky at the moment. Or even directly you can get it from the GitHub. So the tools that you're talking about, where we've compared with pretty much existing stuff, is in the supplementary table S2, which I think I had to get online and show you, which is not going to be a problem. But that's where you should be able to see all the list of softwares with both commercial and academic, free and otherwise. But I don't know if anybody has done it with the games. I think that's
the key of your.
That's our USP for what we are doing. But if you just want to look at a simulator, which is very good, Gemris. I know Bhairav is on this call too, and I'm sure he must have used a bunch of simulators. If he wants to add anything, but I like Gemris. I know recently they have a simulator where you can actually put in a pulseq file and be able to generate things as well.
I just copied the MR Hub link. I think there the ISMR community has at least people have posted quite a bunch of not just the simulations but also recon and other tools.
Yeah, there are so many softwares on that website. Yeah, MR Hub.
It's a good page to even have a look at.
Yeah, that's a fair comment. I'm just trying to see the supplementary table. We collated this for.
Table, yes, one.
So here is a collation of the different kind of softwares, MR simulation software with educational goals basically. Um, way back from 2005 in the language and what you're targeting. And we had our own tool as well in 2019 targeting radiographers at the moment. But yeah, this should give you a sense of the work that's being done leading up until this work here, and what they intended for, and what was the user interface, what programming languages, what features. Yeah, this is probably what we ended up with. But like Vaira was saying, I don't think this list is comprehensive. And I mean, yeah, um, potential software. I think there must be a bunch of commercial ones as well. And this is hardware, which we didn't talk about. But this is mostly for the software and the things. This is the list we compiled. By no means is this comprehensive because I think the landscape keeps changing.
Got it.
RAD, yeah.
Thank you.
This is pretty helpful. Can you share the link of this page as well in the chat or something?
Yeah.
And it was good of you to talk about rotating frame also, because other than physics and chemistry students, nobody else even tries to understand what is a rotating frame. And this has a wonderful link of that also.
Yeah. I mean, I think we have to go back and redo the web deployment a little bit. But if they can earn the stars and are able to demonstrate the definitions. So here this is going on laboratory frame, and we saw a bunch of examples of this. But yeah, you could use this even independently with or without in the classroom setting.
I think it's very useful for teaching point of view and for students' point of view as well.
Yeah, and of course, in another setting where internet is not accessible enough, you can imagine that the students are actually playing by themselves, and getting to from 0 to 1.5, and then they can interact with experts and be able to make sure that the concepts they understand make sense. And we link it up to MRI question and answers for further definitions as well.
Got it. Thank you so much. Senthil sir, you want to add something before we close the session?
It was an excellent start, actually. This is the first webinar we are starting this year. So I would like to thank Dr. Sai for the excellent content here. Of course, glitches are expected everywhere, so that we don't mind. But then the efforts are really supreme. So that's really excellent. I want to thank you for that. And yeah, it's early morning for you. And I'm sure you would have got up an hour or 2 hours before to get ready and settle down and all those things.
Right. Thank you for the opportunity, and we hope we can fix some of these glitches soon. Yeah. Thank you for the opportunity.
Thank you so much, Sairam. I like your T-shirt, MRI for all. Huh?
Yeah. So I was just trying to wear this to promote, building community scanners. This is something that I'm passionate about, and I hope at some point, in India we get an opportunity to build one of these tabletop scanners in due course. But yeah, I want to advertise MRI for all. Here's my shameless shout out to everybody. If you have time, please go to mriforall.org, which will take you to the GitHub website, show you how to build your own MR scanner. Right now, I think it will cost about, in Indian rupees, maybe about 6 to 8 lakh rupees, but you can actually build your own scanner.
Wonderful. So with that, thank you so much, Dr. Sairam. we are closing the session. It was wonderful. We had also some glitches during YouTube streaming because we streamed it on the YouTube also on the ISMRM Indian chapter. So perhaps next time we'll be more careful. Before closing this session, I have just one announcement that I got it from Senthil sir. So the next webinar will be on 21st April. The exact timing will be shared through email, and that will be on the basics of signal processing in MRI reconstruction by Dr. Anshul. He's in Kolkata. So with that, thank you so much. And I think Dr. Senthil sir can take over from this.
Thanks, Dr. Sai and Dr. Durgesh, and thanks to all the participants. We really hope to increase the strength of participation more, and we can make sure that the people working in the field, the PhD students, and the radiographers join the webinars. So we will make sure that that is also being done. Thanks a lot, Dr. Durgesh, for coordinating, and Dr. Sai for the excellent presentation. Thank you all.
Thank you, sir. Thank you, everyone. So with that, we can close this session. Thank you.